Hi, everybody. This is part two. So here we're going to talk about contingency tables. We're really going to talk about contingency tables in the context of something called Bayes' theorem, which is another big, long formula that I think a lot of students kind of get wrapped up on. So we'll take a little bit of time to go through it. So a contingency table is a table used to classify sample observations according to two or more identifiable categories or classes. So in this case, we have 150 adults, and they were asked their gender and the number of Facebook accounts that they used. The following table summarizes the results. So for example, we have people with 0 Facebook accounts broken down by male or female. So there are 60 people with, let me use my mouse here. There are 60 people that have 0 Facebook accounts, 20 of which are male, 40 of which are female. There are 70 people with 1 Facebook account, 40 of which are male, 30 of which are female. And then 2 or more, we have 10 and 10, right? So 20 total, and it's split 50-50. We can also look at this the other way around, right? For men, there are 70 men, 20 of which had 0 Facebook accounts, 40 of which had 1 Facebook, and one out of 7 had 2 or more. So these are really good ways to break down probabilities and to kind of break down of your data by 2 or more of your of these classifying groups. So another way we can display this, right, is with a tree diagram. So we can have something like this, kind of we can make up a contingency table, and then we can plot it, right? So you can have age, broken up here, 30 years old or younger, 30 to 60, and 60 or older. This corresponds with your age groups here, and then you can keep breaking this down. So this is one way to do this. I want to focus a little bit on this Facebook accounts table. We're going to come back in a second and do a numerical example. Okay, so we're going to look at Bayes' theorem, and Bayes' theorem is a method of revising a probability given that additional information is obtained. So this is when you want to find the probability of something that's happened, but you have some information about the situation. I know it's a little bit abstract, but let's just talk a little bit about this in abstract terms, and then we'll narrow it down into more concrete examples and then an actual very current event right now. So Bayes' theorem is super important. It's kind of one of the main reasons why humans are terrible at probability and statistics, is because we don't really understand Bayes' theorem. So for 2 mutually exclusive and collectively exhaustive events, we can write down this formula. The probability of A sub I, which we'll call that A sub 1 and A sub 2, given extra information B here, it's going to be equal to the probability of A. So kind of keep track of this A and this B. And so we're going to have the probability of A times the probability of B given A. So this is a reversed version of this. And then on the denominator, we're going to have, if I is equal to 1, meaning we want the probability of the first event, so A1, this numerator and first part of the denominator are actually identical. So you're really only calculating this one time and then plugging it down here or down here, depending on which A1 or A2 you want to find. So then for A2, we're just gonna replace all the A1s with A2. So the probability of A1 times the probability of B given A2. And we have 2 definitions here. We have prior probability, which is the initial probability based on the present level of information, and then a posterior probability, a revised probability based on additional information. So for example, our prior probability is what's the probability that someone is a male, and then our posterior probability is what's the probability that someone is a male given they have no Facebook account. So let's go back to this table and start to kind of think through how we would do this. So hopefully if you're watching right now, you'll be able to write this formula down and we'll be able to reference it. So let's go back to this contingency table. And if I give you a contingency table, it's actually really easy to do Bayes' theorem because you can kind of just shorthand it. However, on homeworks and exams, I might not give you a table and just give you raw numbers, and you'll have to use the formula explicitly. So for example, if the question I wanted to ask was, what's the probability of being female given the person I'm talking about does not have a Facebook? Well, the way to do this would be, okay, of the people that don't have Facebooks, right? 60 people, what percent of them are women? Well, that'd be 40 out of 60. So 2/3, right? Really easy to do a Bayes theorem problem like that. You don't even have to use the formula, right? As long as you cannot kind of identify what the question is asking and how to look at the table. However, we're going to go through the math on the board later in the future, but also right now, hopefully you'll be able to write this down with me. So the first thing we need to do is we need to identify A1 and A2, and we need to identify B. So remember, we're looking for the probability of female given no Facebook account. And if you remember the formula, it's, maybe I can flip through it here, is the probability of AI given B. So the way I said it was probability of female given no Facebook. So B is going to be no Facebook. And then AI is going to be female. So the first thing we need to find is, what's the probability of female? Well, that's not so hard, right? The probability of being female is going to be 80 over 150, right? That's the probability of being female. And then the probability of B, meaning no Facebook, given female. So the probability of no Facebook given female is going to be 40 out of 80, right? So of women, there are 80 of them. What's the probability of having no Facebook? That's 40 out of 80. So the probability is going to be 0.5. So right now we have 80 out of 150 times 40 divided by 80. And that's going to be our numerator. And if you remember, the numerator here is also going to be down here. So we can kind of write that down twice. So in this slot here, we're going to have 80 over 150 times, for this guy right here, we're going to have 40 over 80. And then the same exact thing on the numerator here. We're going to have 80 over 150 and then 40 over 80. Now for this next one, we have to figure out what's the probability of being not female, in other words, male, and the probability of no Facebook given male. So the same exact exercise. So we're going to have, what's the probability of being male? It's going to be 70 out of 150. And the probability of being male, or sorry, the probability of no Facebook given male is going to be 20 out of 70. So now we have both of these probabilities and we can plug these in. So the probability here is going to be 70 out of 150 for probability of A times this one, which is going to be 20 out of 70. So now that we have our numbers plugged in, hopefully you were able to follow along and write them down on paper, we can do some math. And if we convert it to decimals, on the top, we're going to get 0.265 if we do 0.53 times 0.5, which is those two fractions simplified into decimals. So 0.53 times 0.5, you'll get 0.265 as the numerator. And then denominator, remember the numerator is the first part of the denominator. So we can just rewrite 0.265 on the denominator plus the second probabilities multiplied together. And that's going to end up being 0.1316. So the total fraction is going to be 0.265 divided by 0.3966. And that's going to give us about 67%. And if you remember, 67% is 2 out of 3, or 4 out of 6, or 40 out of 60. So this math works exactly. These probabilities are actually giving us what we wanted to. So this is a really good way to kind of guess and check the results. So there's another example here about disease that you can look up and kind of go through on your own. But something I wanted to talk about in an effort to not be too preachy about this, the Green Bay Packers were just eliminated from the playoffs at the time of recording. This is Sunday, so they were eliminated last night. Aaron Rodgers, the quarterback there, gave a quote about COVID deaths and how he doesn't trust the CDC and he's unvaccinated and things like this. So he's mentioning how the CDC, his direct quote was saying that 75% of COVID deaths have at least 4 comorbidities. So the point he's trying to make is that when you get COVID, there's, you're only going to die if you have other comorbidities. However, the study he's referencing, or the data he's referencing, the CDC study had a group of 1.2 million people vaccinated between December 2020 and October 2021. So only 36 of them had a death associated with COVID-19. So 36 out of 1.2 million died of COVID after they were vaccinated. So yeah, what he's telling you is this posterior probability of 75%. What he's referring to is 28 out of those 36 people had at least 4 of 8 risk factors. So in other words, if they died, they had a very high, they had other risk factors in addition, but the total number of deaths was only 36 out of 1.2. So he's referring to the 78% or the 75% as this posterior probability, as the secondary probability of the probability of death given comorbidities of those people who had already died. So he's looking at a really small subset of people, only 36, and he's making this generalized claim of 75% of COVID deaths, right? That's not the case. The vaccine is working. You have 36 out of 1.2 million people who had died who were vaccinated. So it's really important to get this idea of Bayes' theorem in your mind. And as someone who does statistics all the time, I think that Bayes' theorem is really like a pretty underlying thing for this whole pandemic. If we understood Bayes' theorem a little bit better, I think people would have a better idea of how effective the vaccine really is. But anyway, to conclude this video, there's going to be one more at the end, talking a little bit about combinatorics.